All right, let's get going. So we're just going to finish the section. It's going to be pretty quick. Nothing big. I'm just going to be doing some graphs and talking about the intermediate value theorem. Now you might say intermediate value theorem, Jason, that sounds intermediate. No. This value theorem is the simplest. It should be called the beginner value theorem. Okay. So let's get started. So today we're really getting into the chunk of graphing. We did 5.2. We talked about a ton of stuff about polynomials. Now we're going to use that stuff in polynomials for some exciting results. Okay, so things to include while graphing. I am not going to make you graph these things super precisely. Okay. Yeah, this is the class right before the class you're in, Ashton. Hey, by the way, I've been telling this class how awesome trigonometry is, but they have not been believing me. Ashton, if you just want to share the word, share your experience of how great a class trigonometry is, you know, now's the time to do it, okay? Maybe you'll convince some of these naysayers. They say I'm a liar. All right, so you don't have to have perfect graphs. But there's some things that I need and I will be looking for on graphing problems. Again, this will not be on Thursday's exam. This will be on the quiz, the proceeding the following week. All right. So first off, you should include all the intercepts. All right. The x-intercepts, the y-intercepts, include them all. All right. We've already found those. You should also include the whenever I make a typo, I always try to figure out how to salvage it. You should also include the multiplicity of the zeros. All right, we fixed it. That's super easy to read, right? Multiplicity. Saved. All right. You should include the end behavior. Wow, interesting. We've already done problems to find the intercepts. We've already done problems to talk about the multiplicity. We've already done problems to find the end behavior. This won't be that bad. We've already done all this stuff, though. Did we fix it? Yeah, let's just drop it a little underline. There we go. All right, what else do we need? Should double check the number of turning points. Remember, at most, n minus one of them. If we have too many turning points, we know we goofed. Okay? I am a pen lover. I hate pencils so much. Like, mechanical pencils are garbage. Mechanical pencils, they just, the lead snaps on you. You always got to refill it. It's always hard to get it coming out. Okay. And then normal pencils are so much better. You just get that perfect sharpening. But then it lasts for like 5 seconds. You need to sharpen it again. So we're doing, this is pen math. So only four things. We've already done all this stuff. All right, double check your toilet paper. So let's just do some problems. All right. See, there you go. Trick's actually pretty fun. Thanks, Ashton. Good to hear. We're on example 4. Sketch graphs of the following. And again, this is going to be kind of weird. To do this without graph paper. If you have graph paper, I highly suggest you use it, but I'm not forcing you to use graph paper, so I'm not going to use it myself. Although I have these really cool sheets of graphs. I'll nerd out and show you guys sometime. They're at my office, though. All right. So, part A is going to be the function. I should probably give this f of x equals -2 times x plus 3 squared times x minus 5. So we got to throw it all together, guys. we're throwing all the material together into, and we're just, it's like we've been eating sugar and then eating flour, which doesn't taste very good, and eating butter. But now we're combining it all to make a cake. That's what this problem is, okay? No more flour eating in this class. So that's good news, right? So we need to graph all this stuff. Well, we need to, how do I graph the intercepts if I don't know them? We got to find them first, okay? So we're just gonna do this little by little. It's like those things that you do little by little. Great explanation. Let's go. Find the x-intercepts. All right, so we got the x-intercepts. Remember, the x-intercepts are when y is 0. All right. Oh, no. Don't you dare run out of ink on me. This is my backup pen. If the backup fails, you're really in it for a bad time. All right, so that's when is 0 equal to... When is 0 equal to -2 times x plus 3 squared times x minus 5? I'm going to look for another pen. In the meantime, you guys tell me, I expect you to have the zeros and their multiplicity in the chat when I come back with a new pen. Tell me in the chat, what is the zeros and what are the multiplicity of those zeros? Alrighty then. One of these should work. I've got the mechanical pencil here. All right. You guys, if you did half as much trigonometry as you did whining, y'all would be getting like 120% in this class. Come on. Tell me what the zeros and the multiplicity are here. When is this true? Close. If there were an x here, there'd be one at 0, but there's not. So it's just the -3 and the 5. Good though. All right, so x is equal to -3 and 5. Again, since there's no x here, it's not going to be 0. And you can check your answer. If you plug in x equals 0, you're not going to get that equals 0. Okay. So let's plot those. All right. When you plot those zeros, plot the x-intercepts. Exactly, Lexi. Good. If it were instead, right, if it were -2x times all this stuff, then there would be a 0 when x is 0. But because there's just the 2 is essentially forgettable. Okay. Good. So we plot these x-intercepts. X is equal to -3 is where it crosses the x-axis, and x is equal to +5. Actually, this mechanical pencil writes pretty well. Huh. Interesting. Okay, good. So we've done half of part 1. We found the x-intercepts. We got to find the y-intercepts now, though. So again, the y-intercepts are when x equals 0. So what happens when x is 0? We plug in 0, we get -2 times 0 plus 3 squared times 0 minus 5. Hey, paper, could you be a little longer, please? Thank you. There should only be one y-intercept, because if there's multiple y-intercepts, then it fails the vertical line test and we don't have a function anymore. I really like your positive reinforcement though, Lexi. I love your kind words. Even if it is making fun of me, the way that you say it. Good, Lexi. All right. When x is 0, what do we get? We get -2 times +3 times -5. We just multiply it all together. Okay. So -2 times 3 is -6. Times -5 is +30. This is an excellent opportunity to show something here. Oh, and there's a square here. So that's 90. Watch this. Look at me making a mistake. To show off the fact that when you use a pencil, you can just erase the mistake. Isn't that kind of neat? Whoa. All right. Yeah, thanks for catching that, Stella. So here's a good opportunity to show something off. 90. Well, let's see, where the y-intercept is 90. 1, 2, 3, 4, 5, 6, 7, 8. We're never going to get to 90, right? So you can use a scale, right? So let's say each of these is 20, all right? This is 1, 2, 3, 4, 5. Our graph is going to be a little scaled. 20, 40, 60, 80, 100. So 90 is going to be right there. Perfect. All right. Attendance question for today. We're taking it right now. Early attendance question. What's better, pencils or pens? If you want to specify between normal pencils and mechanical pencils, that's even better. Okay? Take the attendance question right now, pencil or pens. And then we'll go on with solving this solving this problem and graphing this function. Okay? So we finally included the x-intercepts and the y-intercepts. And now we can look at the multiplicity of the zeros. All right? So we found the x-intercepts. They were -3 and +5. The multiplicity of this 0 is 2 because it's got that hard to see exponent. All right? So this multiplicity is 2, right? Our zeros are x equals -3 and +5. This has multiplicity 2. And this has multiplicity 1. So remember what we talked about. Remember what we talked about for what multiplicity looks like. We said there were 3 cases when we're looking at multiplicity of zeros and how they look. Okay? Let's review the 3 cases real quick. So we'll look at a function. We'll have all 3 cases. Let's have something with multiplicity 1, something with multiplicity 2, and something with multiplicity 3. Oh, okay. A little further though. So this is the distinction. If it has multiplicity 1, it crosses kind of normally. This is what happens if it has multiplicity 1. If it has multiplicity 2, we said it bounced off like this. And if it had multiplicity 3, we said it kind of flattened out when it crosses. All right. And then even or odds just kind of look like these with higher, just look a little flatter. Okay. So we're going to use this information. Again, multiplicity 1 looks like this, just kind of crosses, kind of like a line if you really zoomed in on this. Right? If you really zoomed in on this, it kind of looks like a line. Multiplicity 3, if you zoom in on it, it looks like a cubic function. X cubed, multiplicity 3, right? And the other one If you zoom in on a multiplicity 2, it looks like a parabola. That's what we talk about when we say local behavior, right? We zoom in on this function, and it looks like a parabola. It's not a parabola, right? It looks like this. But if we zoom in, that's what they look like. Multiplicity 2 is like an x squared parabola, x squared parabola. Oh, okay. That's where it all comes from. So it all ties together, and it makes sense. You just have to remember it, I guess. All right. So multiplicity 2, we said that's like a parabola. Multiplicity 1, it crosses like a line. How do we include that, though? Right? Does it cross like a line this way, or does it cross like a line the other way? We need to know whether it's going up or down. We need the end behavior. Okay? So let's find that end behavior. So we're going to use this later. We need to use the end behavior. All right. What do we know about the end behavior? What's our degree? What's our leading coefficient? Oh, we need degree and leading coefficient again. We've been doing that a ton. Okay, well, it's not in general form. So it might be kind of hard to find the degree and leading coefficient. I told you, it's like baking a cake. We got to get all the ingredients. If you don't know how to get some flour, you're not going to be able to bake the cake. All right, we're getting some flour right now. All right, so we need the degree and the leading coefficient. This is a cubic polynomial. There's a lot of different ways that we can know that it's a cubic polynomial, but one of the ways to know that the degree is 3 is we can add up the multiplicities. Okay, n is the degree. Good question. All right. A sub n will be our leading coefficient. So if we add up our multiplicities, 2 plus 1, I got this for you guys. The degree is 3. All right. And we need to find the end behavior. Okay. So, what's our leading coefficient? I don't know. You might know the leading coefficient, and it's possible to know the leading coefficient. It's -2, yeah. Good, Delaney. All right. I'm impersonating Lexi, impersonating me. Good, Lexi. Good, good, good. So if you didn't know it was -2, you could FOIL and put f of x in general form. It's a little bit of math, but if you don't mind math, you could go ahead and do it. The leading coefficient is -2. So, what does the end behavior look like if it's odd and the leading coefficient is negative? Okay. It looks like a negative cubic function, the end behavior. You can go back to your table. If it's odd, they go in opposite directions. Because it's negative, it means it goes down to the right. Negative means down on the right. Odd means opposite directions. That's our end behavior. Oh, that's great. Now we know which way it's going on the right. It's going down on the right. So, look. This 0 has multiplicity 1. Multiplicity 1, we said, looks like this. Crosses kind of like a line locally. Multiplicity 3 crosses like a cubic locally. Multiplicity 2 crosses like, well, it doesn't cross, it bounces off like a parabola locally. So, it's going down on the right, and it's crossing kind of like a line. So it's going to look something like this locally. We don't know what it's going to look like in the big picture, but we know somewhere it's going to look kind of like that. Just around there, it's going to look something like that. We're just filling in pieces by piece. We're like the three blind mice, except it's the one blind mouse. And we're just looking at it. So we felt the trunk of the elephant. We felt the butt of the elephant. We felt the feet of the elephant. And we're just putting it all together to figure out that it's an elephant. Yeah, Lexi, draw this on yours as well. Mm-hmm. Yeah, so Gabe, the multiplicity. So multiplicity is something that has to do with zeros. So we said the zeros here are -3 and 5. The multiplicity is essentially the exponent for that factor. We may or may not review. Tomorrow we'll review for the exam though. Okay. So -3, that factor as a multiplicity has an exponent of 2, so we say it has multiplicity 2. Then x minus 5 is 5. That has an exponent of 1, so that's the multiplicity of 1. Okay. That's where that comes from. So let's use the other multiplicity. Multiplicity is 2. So we're gonna have some sort of parabola here. Either a mini parabola that opens up, or a mini parabola that opens down. How could we possibly know which one it is? Well, on the one hand, right, we need to be up here at 90. On the other hand, we also know the end behavior goes up to the left. So we know if we're having a mini parabola, it has to be going up on the left. So if this looks like a mini parabola, it's going to look something like this. Yeah, good, Lexi. Good. Well, now, what have we included? What do we know about this graph so far? We know the intercepts. We put the intercepts everywhere. We know the multiplicity. We included the multiplicity, mini parabola, because it's even. Kind of like a line, because it's 1. End behavior, we know that as well. Right? To the left, it's just shooting to the moon. To the right, it's falling down. Great, we included the end behavior. All right, Lexi, you're good. So let's just connect the dots. Parabolas are smooth. Okay. They have curves. So just fill this in as you want it to be filled in. All right. So who knows? Maybe it looks like that. Maybe it doesn't look like that. Who knows? You're just sketching. You're just getting an idea of what it looks like. Okay. Maybe it looks like that. We don't have an easy way to find where this turning point is. Not yet. But if anyone ends up taking calculus, there's a really easy way to find where this turning point is. You just take the derivative of the function. Derivative is the slope. The turning point is where the slope is 0, a little piece of flat. You just can solve that equation. But we're not in calculus, so do that some other time. So that's how you do these problems. All right? It takes a long time. You got to find out a lot of things about these problems. Okay? Any questions before I move on? Because we're going to do another one. Okay. Oops. When we were trying to get our pen to flow, we ran into some issues. So a sub n, that's our leading coefficient. It's -2 because once we expand everything out, the only number that gets multiplied by the x's is going to be a -2. Another way to show it real quick, right, is f of x equals -2 times x plus 3 squared times x minus 5. If you FOIL out this perfect square, you get x squared plus 6x plus 9 times x minus 5. And then, then you have to multiply this one out as well. You get x cubed plus 6x squared plus 9x minus 5x squared minus 30x minus 45. And now you can see where the -2 comes from. Because the leading coefficient is the coefficient next to the x cubed. Because x cubed is our highest power of x. And the number that gets multiplied by it, again, we'd do another step if we wanted to put it in general form. The number that is multiplied by that x cubed is that -2. All right, so that's kind of why. If you want to put it in general form, Lexi, then yeah, you multiply it out. Okay, and so you FOIL first, and then you gotta, this is not even foiling, it's like triple foiling or something like that. Multiplying everything in here by everything in here. And then you'd have to distribute that -2 and collect like terms. That's only if you want to put it in general form. If you can find the leading coefficient without putting it in general form, you don't have to put it in general form. It just makes it, it's just a couple extra steps of algebra to make the leading term easier to find. You would distribute the -2, Sochel. It's just, I didn't want to do it. You'd collect like terms and distribute the -2 next. Good question. Other questions? These are good. Keep them coming. Oh, my throat is very dusty today. All right. Example 4b. Sketch the graph of g of x equals 1/4 x times x minus 1 to the 4th, whoa, times x plus 3 cubed. So we got to just go through that list of things that we need to find, right? We need to find the intercepts, the multiplicity, the end behavior. Double check the number of turning points. Okay, this is a cubic function, so it has at most 2 turning points. And it does have 2 turning points, right? There's a turning point right here and a turning point right there. So let's find the intercepts. Let's find the end behavior. Let's find the multiplicity. Let's slowly add it to the graph. Okay? Oh, that is a curvy axis. All right. So intercepts. So this, again, this first part is always a little tricky. Okay. The first part is always tricky. Does this have an x-intercept of 0? The other one didn't have an x-intercept of 0. Does this have a 0 at 0? Which case is this? Because they're kind of confusing. Sometimes it's 0, sometimes it's not a 0, and there's a distinction that we slightly talked about for when we have it. And the answer is that yes, because there's an x right here, there's a 0 at 0. Because there's an x out in front, if x is 0, this whole thing gets multiplied to become 0. All right. X is also equal to 1 is a 0, and -3 is also a 0. All right, Ashton, if you got to leave, don't worry. You can always come back to watch the video of college algebra. You can come back and get some more. Let's do multiplicity while we're here. This has multiplicity 1. The exponent is 1. This has an exponent of 4. It's going to be a multiplicity 4. This, multiplicity 3. Multiplicity is just the exponent. Ooh, we got a multiplicity of 3, 1. We didn't have that case in part A, but it's going to be okay. So let's include these x-intercepts. X equals 0, that's 1. X equals 1. That's here. Oh, should have made my graph a little bigger. And -3. Hold up. I've got a pencil. Watch this. We're going to zoom our graph a little bit. This is kind of fun. 1, 2, 3. 1, 2, 3. Now we'll have a little bit more space to show what's going on. All right. So our zeros are at 0, at 1, and at -3. All right. Good. Multiplicity. We can't talk about multiplicity yet until we know the end behavior, because we don't know whether this line goes like this, up, or like this, down. So let's talk about end behavior. Okay. We need to know the degree n and the leading coefficient. Again, degree, just like we said before. If you find the multiplicities, the degree is easy. You just add up all the multiplicities and you're going to find that degree. All right. Unfortunately, it will not work for a college degree. So multiplicity is 1, 4, and 3. Multiplicity is 8. Whoa, that's a big one. Okay. And a sub n. Now, I mentioned you can always put this in general form to find what your leading coefficient is. Putting this in general form would really take a while, right? This is raised to the 4th power. You'd have to like essentially foil, superfoil, I don't know what the word is, 4 times. This you'd have to superfoil 3 times and then multiply those super polynomials together. It's going to take a long time. But if you just think about how foiling works, you can get to the leading coefficient. We added up all the multiplicities to find our degree. 1 plus 4 plus 3. Because if you add the multiplicities, you always get to your degree. Good question. So again, notice that no matter how many times we multiply a binomial like this by itself, we just get x times x's for our biggest term. The coefficient of this is never going to be anything other than 1 when you multiply it out. The coefficient of this leading term is never going to be bigger than 1. And then when you multiply it all together, it will get multiplied by a 1/4. So your leading coefficient here is 1/4. It's not always what's on the front though. For example, off to the side, real quick. If you had something like this, right, your leading coefficient is not 2. Because when you FOIL this out, you get a 4x squared. So your leading coefficient here is 4, right? If you had something like this, you'd have to multiply a whole bunch. You'd have to multiply it by itself 3 times. Your leading coefficient would be 8, 2 cubed. And the number doesn't really matter. You don't need to find the leading coefficient. It's good practice, but you don't really need the leading coefficient. What you really just need to know is the leading coefficient going to be positive or negative? That's the important thing. So if you don't want to know 1/4, all that matters is that you know it's positive or negative. All right. There's a lot of neat uses of pencils. I'll tell you guys. Who knows? By the end of the semester, I might even be cooking eggs on a frying pan. Not likely. Who knows though? People change. So we know the degree is even. We know the leading coefficient is positive. Because it's positive, we know it's going up on the right. Because it's even, again, positive means up on the right, negative means down on the right. Because it's even, we know it goes the same direction. This is kind of our end behavior. Woo! All right. So we know the end behavior. So now is the real hard part. Combining the end behavior. Oh, we never actually found our y-intercept. Combining the end behavior with the multiplicities. Okay. The y-intercept is also 0, though. I should specify that. Right? Remember, like we said yesterday, if the x-intercept is 0, the y-intercept is also 0. So let's look at this 0 right here on the right. What's the multiplicity of this 0? The multiplicity, the 0 is 1. The 0 is 1. The x-intercept is 1. We're looking at this guy with multiplicity 4. What does multiplicity 4 look like, remember? If we have an even exponent, it looks like a parabola. If we change this to 4, it's not going to look that different. Notice how it just gets flatter right here? This is the 0 we're looking at. If I change it between 2 and 4, just makes it flatter, but it still kind of bounces off. If it's even, it bounces off. Okay, we're going to use that information about the multiplicity. All right, so right here, it's even, it's going to bounce off. Is it going to bounce off up or bounce off facing down? And we know that because of the end behavior. It's got to be going up on the right. So it's going to be something like this, and again, it's kind of flat. Good, Lexi. All right. So we know this for that 0. Again, we're only looking at little baby pieces. Also, we know the end behavior, so we know it goes up forever. All right, let's look at this 0. That's the x-intercept of 0. It has multiplicity of 1. So it means we have to cross like a line. And we know that we cross up, not down. We know it crosses up because it's got to get to here. It's got to connect. It's like I used to play Roller Coaster Tycoon growing up. You design roller coasters, and I designed 2 parts of a roller coaster, but if they don't connect, we got a problem. This is like a roller coaster. Although if you make a roller coaster like these polynomials, it will literally kill people. Okay, so this has a multiplicity of 1, this x-intercept. So it's just going to look kind of like a line. We'll worry about connecting these things later, just like with roller coasters. All right, last 0 is this guy over here. The x-intercept of -3 is multiplicity 3. Multiplicity 3, right? Looks like a cubic function. We're going to have this situation. Good for roller coasters. All right, and the question is, which way does it face? And yeah, it's going to go up on the left and down on the right. Okay? So last thing, it's cubic, so it knows it's going to go up on the left and down on the right, kind of like a cubic function. Again, when you're plotting this multiplicity stuff, it should look like either a parabola, a line, or a cubic. Odd multiplicities, like a cubic function. Multiplicity of 1, like a line. Even multiplicities, like a parabola. And now we just connect the dots. Okay? So maybe it connects this, again, make sure you keep it curvy. Maybe this connects like that. Maybe it doesn't, but we're just sketching. We're not doing exact graphs. We're just sketching, giving ideas of, what does this kind of look like? And again, maybe this curves around and goes like that. Yeah, it's a scary roller coaster for multiple reasons. It goes on literally for, the domain of this is -infinity to infinity. It goes on literally forever, so that's not a great roller coaster. There's no place to get on the roller coaster either because there's no start or finish. And it has an infinite drop, which is really not recommended. But let's compare our sketches. Let's see how we did. Okay, before we finish the section with the intermediate value theorem. Again, they're only supposed to be sketches. They're not supposed to be beautiful works of art. I'm a little nervous, but let's see what it looks like. All right, 1/4 times x minus 1 to the 4th power times x plus 3 cubed. Okay, so it looks kind of similar. Let's put these side by side. Hold on. Let's put these side by side. All right. This one, we have the right shape, right? The shape is the right. But yeah, it goes really far down. Okay. It really drops. Okay, so not exactly the same, but pretty close. This is a roller coaster, like. All right, so it's a good idea to check your answers. Good. Let's talk about the intermediate value theorem. Down to the bottom ocean. Yeah, this roller coaster goes down to the bottom ocean, pick up anyone who's down there, and bring them back up. Okay. So what we're talking about next, we've kind of really already talked about a little bit. I haven't told you what we were talking about. It's called the intermediate value theorem. And I never like writing it. It's too long. So I'll be saying IVT. I don't even like saying it. The intermediate value theorem. So essentially what this theorem states is what we've already been doing for the graph, right? Remember for the graph we said, what did we say? We said, okay, I know we have a parabola here. I know we have a line here. Well, they got to connect somewhere. That's essentially the intermediate value theorem. If you know you're here and you're here, they somehow got to connect. Okay? So let's give the theorem and then talk about it. For a polynomial function, f, two cases. Case one, if f of some point A and f of some point B have opposite signs, then we can say something, right? Let's look at this. We're not even going to finish it just yet. Let's look at this. We're doing a polynomial. And I don't know, let's say A is over here. Let's say B is over here. So if they have opposite signs, that just means one of these function values is positive, one of these function values is negative. So maybe we're up here and we're down here. The intermediate value theorem just says, well, if I have a polynomial and I know I'm up here and I know I'm down here, there has to be some way of getting between them. There has to be an x-intercept between these 2 points. There's no way to connect these 2 points for a polynomial that does not cross the x-axis. So that's the intermediate value theorem. All right. There's at least 1 0 between A and B. And again, maybe there's a lot of zeros. Maybe it goes wee-oo, wee-oo, wee-oo. Or maybe there's only 1 0. Maybe it just goes straight over. We don't know. But the intermediate value theorem says we do know that there's at least one of them. All right. Part 2 is the sad part. It's the part where you cry. If f of A and f of B have the same sign, then we know nothing. Okay, it's inconclusive, right? If this were the case, if they were both positive or they were both negative, well, yeah, maybe we cross, but maybe we don't. We don't know whether we cross the x-axis. This theorem doesn't tell us anything. So notice, right? If they're opposite signs, there is a 0. If they're the same sign, though, we do not get the opposite conclusion. There's no conclusion with this one, right? So if they're opposite signs, we know what's going on. If they're the same signs, we know nothing. So let's do the last example of the day. Oh no. So I was looking at my notes. And isn't this kind of sad? In my notes, I write the example problems that we're going to do, so I know what we're going to talk about and stuff. I had an example 6 here, just for fun. But the example 6, just for fun, we're missing the just for fun today. We're only doing work. No just for fun today. I'm sorry. I apologize. I have failed you as a math instructor. All right, so last example problem, example 5. Use the intermediate value theorem to, part A, show that f of x equals x cubed minus 5x squared plus 3x plus 6 has at least one zero between x equals 1 and x equals 4. Phew. Use the intermediate value theorem. How am I supposed to use the intermediate value theorem? I don't even know what the intermediate value theorem is. So we go back to it and find our notes. Say, well, what is the intermediate value theorem? Also, I was lying to you guys. I do know what the intermediate value theorem is. So we need to show that there's at least one zero. So notice, if f of a and f of b have opposite signs, boom, there's a zero. So we just need to find, do f of a and f of b have opposite signs? What are f of a and f of b? What's a and b? We need to answer those questions. Okay? So our a here is something, and our b here is something. We need to identify what those are. Once we do that, and tell me what they are, you guys know what, oh, sorry, I gave it away. Someone tell me what they are. Then we need to find what is f of a and what is f of b. If they have the opposite signs, one's positive and one's negative, then we'll say, boom, IVT, slap. Slap the IVT all over this problem, we'll be done. It is 1 and 4. I'll blame that second answer on my handwriting. But yeah, it's just the 1 right here and 4. Okay, because we want to find a zero between these 2 points. So these are going to be our a and b. Okay. So f of a, right? That's just f of 1. A is 1. They're the same thing. We just replace it. All right. So we get 1 cubed minus 5 times 1 squared plus 3 times 1 plus 6. Plug that into your calculator. You get 1 minus 5 is negative 4, plus 3 is negative 1, plus 6 is 5. If you plug it into your calculator. Oh, it doesn't matter what a and b are. Although, good question. It's not a and b that matters. It's f of a and f of b that matter. And that's a very good distinction, so I'm glad you brought that up. The 1 and the 4 are just from the just the problem. It's just asking you to use the intermediate value theorem. It gives this to you. So what we have right here, f of b is just f of 4. So again, this is positive. Hopefully this is negative. If this is not negative, we're going to have a problem. So what is f of 4? That's going to be 4 cubed minus 5 times 4 squared plus 3 times 4 plus 6. So again, type that into your calculator. You're going to get 64 minus 80 is negative 16 plus 12 is negative 4. All right, I need to use a calculator because I think I'm doing it wrong. Right? We have 1 cubed minus 5 times 1 squared plus 3 plus 6. That was indeed 5. This one is 4 cubed minus 5 times 4 squared plus 3 times 4 plus 6. Nope, that's 2. Wait a minute, what did I do? X cubed minus 5x squared plus 3x plus... So for those of you who do not understand my confusion right now, my confusion is that, right, the problem said use the intermediate value theorem to show that there's a 0. But as we've done it, they're both positive. We don't know anything. I think I may have written down the problem wrong. Use the intermediate value theorem to show x cubed minus 5x squared plus 3x plus 6 is at least one 0 between x equals 1 and x equals 4. Okay. Well, this is fine. They're both positive. We'll just change the problem. Using the intermediate value theorem to try to use the intermediate value theorem. They're both positive. There's no conclusion to the intermediate value theorem. No conclusion. All right. Curious what happened, but it's not that important, okay? So, part B. Do the same for this one. How about f of x equals 7x to the 5th minus 9x to the 4th minus x squared between x equals 1 and x equals 2. You know the really funny thing about this? If we chose b to be -5, like Delaney said, it would have actually worked out. So we do the same thing. Again, what is our a? Our a is 1. What is our b? Our b is 2. We need to say, what is the function value at these 2 points? Do they have the same sign, opposite signs? If they have the same sign, we say, well, I don't know. Intermediate value theorem doesn't say anything. But if they have opposite signs, then we have our conclusion. So, f of a, we plug that in, right? That's just f of 1. Plug in 1. Get 7 times 1 to the 5th, minus 9 times 1 to the 4th, minus 1 squared. That's 7 minus 9 is -2, minus 1 is -3. F of b, that's just f of 2. b is 2, the same thing. Plug in 2, you get 7 times 2 to the 5th times 9 times 2 to the 4th minus 2 squared. Type that in your calculator. You can get 32 times 7, which is 224, minus 9 times 16. All right, let's not do this. 7 times 2 to the 5th minus 9 times 2 to the 4th minus 2 squared. It's going to be a 76. So look, this is negative. Look, this is positive. Whoa, how exciting. All right. What's the conclusion? They have different signs. So there has to be a 0 between 1 and 2. By the intermediate value theorem, there must be a 0 between a and b, which is 1 and 2. Kabam! All right. That's how you use the intermediate value theorem. Same sign, no conclusion. Opposite signs, there has to be a 0 between the 2 x coordinates. All right. Last thing I want to talk about real quick before you do your quiz, right? Really quick, is talk about turning points with some just lingos, informal definition. If we have some kind of polynomial, right, we said the turning points are right here, and right here, just where it turns from going up to going down, the hills and the valleys. We also have a different name for the hills as we do for the valleys. So these are called local minima. The plural of minimum, apparently. Hold up. Wait a minute. I think we need Delaney to take over the class because this is not a minimum. Ooh, good thing we got this handy dandy pencil. Local maxima. Max, big. This right here is called the local minimum. All right, the singular is the plural is All right. These are turning points. All right. And that's the section. Perfect time for you to go and take your quiz right now on 5.1 and 5.2. We'll have an exam on Thursday. We'll have a review tomorrow. I actually did decide, somebody suggested Zoom, and I said, no, let's not use Zoom. I've changed my mind again. Tomorrow, for our video lecture, for the review session, we are going to be Zooming. Okay? So I hope there's some Zoomers in this class. I'll share the link via Canvas as well as Discord. Okay? Tomorrow review will be Zoom for the exam. All right? Thanks for I don't know what I'm going to thank you for. Good luck on your quiz. Okay? Bye-bye.